Okay, guys. So the exercises for this chapter really are just going through stuff that we did in the lecture. So remember, we started off, we said we wanted to calculate this integral in. So instead of calculating in, we said that's in is an infinite number of integrals. You have to calculate it for each positive integer n. So we said instead of doing that, let's calculate I of b. That's a single integral to do. And the good thing is, if we take derivatives of I of b with respect to b and set b is equal to 0, we get hold of in. So I of b, we usually call a generating function, and it generates the integrals in, okay? And the one integral we were able to do was I naught. In doing this integral for I of b, here's just the logic. The logic is that for I of naught, the integrand, the exponent of the integrand is a parabola centered at the origin, whereas for I of b, the exponent is a parabola centered at some axis that's shifted away from the origin. We then shifted the axis back to the origin, and we found that to do I of b, we needed nothing more than to know I of naught. We repeated precisely the same logic for the path integral. So we want to calculate all of these correlation functions, integral d phi e to the is, and then a product of the fields phi. We said instead of calculating that, let's calculate z of j. Z of j is often called the correlation generating functional, or the generating functional of correlation functions. And why? It's because if you take functional derivatives of z of j with respect to j and then set j is equal to 0, you get exactly these correlation functions. If we study z of naught, this is just the integral d phi e to the is. That has the interpretation of the overlap of the vacuum with itself. So we can set that equal to 1. Setting that equal to 1 is equivalent to choosing a normalization for the path integral measure. And we decided to calculate this now for the free theory. Notice that the action for the free theory is quadratic in the fields phi. It only depends on phi squared. And that's the property that our in integral in one dimension had too. The phase was simply phi squared. We then evaluated this. What we did was we looked at where the peak of the integrand is maximized, and we called that field value phi naught. Then we shifted by phi naught. So we're just following the logic of the one-dimensional integral, and we found that to do the path integral, after we performed this shift, all we needed to evaluate was z with j is equal to 0. And we know that that's the overlap of the vacuum with itself, so we've set that equal to 1. So we were able to get hold of this answer for the path integral as the last box in this lecture. Of course, we still need to calculate phi naught of x, but calculating phi naught of x just amounts to solving an ordinary partial differential equation, and we're going to see it's not even a very difficult partial differential equation to solve. So that was the complete logic, okay? And the exercises are just asking you to carry out some of the steps of this logic on your own. So I think it's very important that you can go through this argument, you can follow each and every step, and you can fill in all of the details that are required. Very good. Let's now move on to the next chapter, where we'll actually solve for phi naught of x.